Welcome to this episode of Real Chemistry. Today we're going to be talking about how nuclear bombs work. In particular, we're going to focus on how nuclear bombs work if they're made out of uranium or plutonium, two different materials that can actually undergo a fission chain reaction, which turns out to be central to having a nuclear bomb work. Here you see two pictures of really famous nuclear bombs. On the left there, you see Little Boy, and on the right, you see Fat Man. These are two different types of bombs, and it turns out that the one on the left is made of uranium, and the one on the right is made of plutonium. And at the end of the video, you'll be able to understand why they have these different shapes to make bombs out of these different materials. Let's start with the uranium bomb. So the uranium bomb is based off of a nuclear chain reaction where you need the isotope uranium-235. So that's a special version of uranium. And if you hit it with a neutron, it splits apart and releases more neutrons, which can either hit uranium-238 if it's around, which it usually is, hit another U-235, or exit the material. If it runs into another U-235, then it can lead to a chain reaction where we get more and more fission events. And each time you have a fission event, you have a release of a large quantity of energy, because nuclear reactions convert some mass to energy, and that turns out to release way more energy than a standard chemical reaction does. So here is the main challenge for a nuclear bomb. If you want that special type of uranium, uranium-235, which can undergo fission reactions, you have to enrich uranium. If I just go into the earth and get a piece of iron ore, so that's a chunk of iron ore, only about 1% of the uranium in that ore will be uranium-235. And so if I try to have a nuclear bomb made directly out of raw uranium, it won't work because neutrons will just run into other U-238 nuclei. There's too many U-238 nuclei around and there'll be no chain reaction. So what you have to do is enrich it. And that means what you do is you take a mixture of U-235 and U-238 and you sort it. So you separate out U-235 from U-238. You can do that for a little while and you get what's called low enriched uranium, which is about 20% U-235. This turns out to be what you use in like a power plant. So if you're using nuclear power. If you want a bomb, you need to enrich it to 85% plus. And the reason that matters is that the more U-235 there is there, the more likely that any neutron flying around will run into U-235 and cause another fission event. Whereas the more U-238 there is around, the more likely a random neutron will run into that and shut down the reaction. So the main challenge of the uranium bomb is actually obtaining enough enriched uranium. That's a really challenging thing to do. If you want to do this, you need huge numbers of these calutrons to make just one nuclear weapon. In fact, a facility in Oak Ridge, Tennessee during World War II ran for the entirety of the Manhattan Project, that is the time they were working on the nuclear weapon, to produce enough uranium for just one bomb. That's all we got by the end of World War II. So it's a very slow way to produce uranium-235, but it can be done. The more modern way to produce uranium is with something called gas centrifuges. We won't talk about this in detail, but basically they use the same principle of the fact that U-235 is lighter than U-238, and they make a gas of uranium, and they spin around that gas really fast, and the heavier uranium tends to go towards the outside of these cylinders, whereas the lighter uranium-235 tends to stay towards the center. So in the modern era, it's much easier to do this. But the main challenge, nonetheless, is to obtain that highly enriched uranium. Okay, so once you have uranium, you don't just need it to be pure enough. You don't just need enough U-235. You also need a large enough chunk of it. Because remember, in addition to running into U-238, the other thing that can happen is it can just exit the chunk. So you need a big enough block of it. That block turns out to be what's called a critical mass. So here we see in the top sphere a subcritical mass. And what characterizes a subcritical mass is that every neutron on average will only cause one other neutron to be produced. And that means over time the number of neutrons don't increase. So it just kind of sits there and is stable. On the other hand, if you get a big enough chunk, then you go ahead and make a critical mass. And that's where you start to get chain reaction, where each neutron produces more than one neutron. So one way to think about this is right here, we cut out this pathway by enriching uranium. That means that there's not these dead ends for our fission chain reactions because we've gotten rid of the U-238. Right here, that's the pathway where we exit the block of uranium. We get rid of that pathway by having a big enough chunk of U-235. And if we have those two things, a big enough chunk of U-235 that is mostly U-235, about 80%, then you get a chain reaction. But here's the problem, right? Say I just have a big old chunk of it that's at a critical mass. That makes a bomb and would explode. So the last challenge to the nuclear bomb, the uranium type nuclear bomb, is to make a critical mass only when you want the bomb to go off. How do they do that? Well, this is where the gun type assembly comes in. What happens is we use just a regular old explosive to bring two halves of subcritical U-235 together. So both of those semicircles there, those half spheres, represent U-235 that's smaller than critical mass. That means there's no chain reaction going on there. And that explosion brings these two halves together, and when they come together, that makes the bomb go off. So we use a conventional explosive here on the left side. This is not a nuclear explosion, just to drive the two halves of those spheres together. This is actually a pretty easy process. So the main challenge, again, is obtaining enough of that U-235. And now we come back to looking at our pictures of our bomb, and we can understand why this has this long shape, because it's a gun type bomb where the two halves are shot at each other. All right, what about our plutonium bomb over here? Well, it turns out that obtaining plutonium is actually the easy part. So obtaining the material is hard for a uranium bomb, but easy for the plutonium bomb. All you have to do is take uranium-238, combine it with a neutron, and you get plutonium-239. Turns out there's also two beta particles that come off called beta decay, and some intermediates that go into that. But the main takeaway point is if you get U-238 and you hit it with neutrons, you get out plutonium. And so uranium-238 is the easy one to find, and we just get a source of neutrons to fire at it, and we can make as much plutonium as we want. So that's actually the easy part. The hard thing is that plutonium can't be used in a gun-type assembly. The reasons for that are because plutonium's actually better at undergoing fission. And that means those two halves, if you were to fire them at each other in the gun-type assembly, actually start undergoing a chain reaction before they get very close together, and the bomb basically fizzles out. And so instead of using a gun type assembly, you have to do something else. You have to use an implosion type assembly. So what you do is you have this plutonium here in the center, and you have to set off a bomb, a conventional explosive, all the way around the plutonium. Here's the trick though, it has to be imploded exactly symmetrically. That means if the explosives on the right go off just a little bit later than the left, it doesn't work. Why is that? Well, that's what we call a cannon, right? So if this half explodes and the other half doesn't, this little plutonium core is just going to shoot out and it's not going to implode. So the trick is you get those explosions to go off all at once. And that makes our plutonium core really small. And that actually is another way to get our critical mass. And then you have a nuclear explosion. So the main challenge is that symmetrical explosion around the plutonium core. It's how you get a critical mass, and it's also the main challenge. It's very challenging to do that technologically, to have all of those explosives go off at exactly the same moment. All right, so here's just a comparison of our two different types of nuclear bombs we talked about. The gun type uses the fuel uranium-235 and a fission chain reaction. You can obtain that fuel, the uranium-235, by centrifuge, and the main challenge is actually getting that fuel. Meanwhile, the implosion device uses plutonium-239 and still a fission chain reaction. The fuel is easy to obtain, relatively speaking. You just bombard uranium-238 with neutrons, but that symmetrical explosion there is the main challenge. Thanks for watching this episode of Real Chemistry.